Welcome to the Deep Dive, where we explore fascinating corners of mathematics. Today, continuing our journey through the Online Encyclopedia of Integer Sequences, the OEIS, we're setting our sights on a sequence with a rather evocative name, A000183, the discordant permutations.
Indeed. Discordant permutations. It was previously cataloged as M2121N0838. It offers us a glimpse into the subtle world of combinatorial arrangements. The initial terms, 0001222144, they already kind of hint at a structure that's, more intricate than it might initially appear.
Right.
So our goal today is to really understand what makes a permutation discordant in this specific sense and maybe uncover some of the interesting places this concept leads us within combinatorics.
Okay, so a permutation, as we know, is just a rearrangement of elements. If we're talking about a set of n numbers, say 1 through n, a permutation is one specific order they can be written in. Now, what twists things makes it discordant?
Well, a discordant permutation of length, as defined for A000183, is one where none of the numbers appear in their original position. Think of it like this. If we start with 1, 2, 3, a discordant permutation would be something like 2, 3, 1. See, 1 isn't first, 2 isn't second, 3 isn't third. But 1, 3, 2 wouldn't be discordant because the 1 is still in its original first position.
Got it. Fixed points are forbidden.
Exactly. So at its heart, the study of discordant permutations is about understanding permutations when fixed points are forbidden. It's a fundamental constraint that, pops up surprisingly often. This is directly linked to the classic idea of a derangement, which is exactly a permutation with no fixed points. The problème des rencontres, a classic puzzle. Mismatched letters and envelopes.
Oh, wait.
That's essentially asking for the number of derangements. Berman and Fryer's work from 1972 goes into more detail on derangements if you want to dive deeper there.
That makes perfect sense. It's about everything being displaced. Now, the OEIS description also mentioned...
Scenario with diners, yes,
Right.
around a circular table.
Right, that sounds like it adds another layer of complexity.
It does, yeah. The combinatorial interpretation given in the OEIS presents n as the number of ways to reseat n diners at a circular table, such that no one ends up in their original seat or in a seat immediately adjacent to their original one.
Oh, okay. So not just not in your original seat, but also not next to it either.
Exactly. That additional restriction not being next to where you started distinguishes this specific type of discordance from a simple linear derangement. The circular arrangement introduces neighbors, making the conditions more stringent.
So those initial zeros in the sequence for N1s, 2, and 3, those probably make sense under this circular table rule, right?
Precisely. Yeah, think about it. One diner, any other seat is still adjacent. Two diners, if they swap, they're now next to where they began.
Okay.
And for three diners, if one moves one seat over, they'll be next to their original spot, left or right. It's not until we have at least 4 diners that it actually becomes possible for everyone to move, so they're neither in their original chair nor a neighboring one.
That clarifies the start of the sequence nicely. Now, for N5, the sequence gives away A5 equals 2. An example. Original 1, 2, 3, 4, 5 leads to 3, 4, 5, 1, 2, and 4, 5, 1, 2, 3. Looking at those, it's not immediately obvious why only those two work under the circular condition.
You're right. It requires a bit of careful checking. Take 3, 4, 5, 1, 2. If we look at the original positions, 1 has moved 2 places, right?
Yeah.
So if 2, 3, 4, and 5 all shifted 2 places cyclically, so no one's in their original spot or next to it. And the same logic holds for 4, 5, 1, 2, 3. Everyone shifted by 2 again, just the other way.
Okay.
If you try to construct other permutations of 1, 2, 3, 4, 5, satisfying this no original seat, no neighbor rule, you'll pretty quickly see why there are only these 2. It highlights that even for small numbers, these constrained counting problems can get quite subtle.
It certainly underscores that this isn't just a trivial counting exercise. Now, I recall seeing a mention of concordant and discordant pairs in statistics. Is that related?
It uses the word discordant, which, might suggest a link, but it's actually a different concept. In statistics, when you analyze pairs of data points for 2 variables, a discordant pair means the relative order of values in one pair is opposite to the relative order in another. Like if person A is taller and heavier than B, but person C is shorter but heavier than D, that involves a discordance between height and weight.
Right, I see.
So if we viewed a permutation as pairs, IA, a discordant pair of permutations in that statistical sense would involve elements changing relative order between them. It's about the relationship between permutations, not the internal property of one permutation relative to its start, which is our focus with A000183.
Good distinction. So same word, different mathematical job.
Exactly. It's a good reminder.
That's an important distinction to make. Thanks for clarifying.
Got it.
The outline also mentions the problème de ménage, the married couples problem. That sounds like a classic headache of a combinatorial problem.
It is indeed a classic. And yes, a headache sometimes. The Menage problem asks for the number of ways to seat married couples around a circular table, such that men and women alternate, and crucially, no one sits next to their spouse.
Oh, boy.
Yeah. The elegant solutions, pioneered by folks like Lazan, Moreau, Taylor, they crucially rely on the concept of discordant permutations, specifically in that circular arrangement context with forbidden adjacencies, the no spouse sitting next to each other constraint. When you look at it from one gender's perspective relative to the other, it becomes equivalent to finding a permutation where certain neighbors are disallowed. It's a form of discordance.
Wow. So this seemingly specific idea of discordant permutations is actually a key ingredient in solving a much more complex and, frankly, relatable problem like seating arrangements.
Exactly. There's even a recurrence relation and a closed form expression, Touchard's formula for the solutions the Menage numbers in.
Yeah.
The first few are 0, 1, 2, 13, 80. That's OEIS A000179 if you're keeping track.
Is 00179. Got it.
The number of valid seatings for the couples is directly tied to these Menage numbers, which are built on these principles of circular discordant permutations.
It's really remarkable how these abstract objects have such concrete applications, even indirectly. Now, shifting gears slightly, 4 discordant permutations. From Whitehead's work, how does that fit in?
Right, so 4 discordant permutations basically takes the idea of displacement a step further. In a 4 discordant permutation, one gene, an element I can't be equal to I plus 1, I plus 2, or I plus 3. And those indices are mod n for the circle.
So even more restrictions, not just the spot or the neighbors, but the next 2 spots after that too.
Exactly. Not original, not next, not 2 away, not 3 away. The permutations in A000183 are less restrictive, just forbidding the original spot and immediate neighbors. By exploring these stricter conditions, like 4 discordance, we can, uncover even more refined structures within permutations.
It sounds like by increasing the discordance level, we're imposing stricter constraints. The abstract mentioned rook polynomials and hit polynomials. Are those the tools for analyzing these?
Yes, rook polynomials and hit polynomials are powerful tools here, especially for permutations with restricted positions. Think of a rook polynomial like a generating function. It counts ways to place non-attacking rooks on a board where some squares are forbidden.
Okay.
In the permutation context, the board represents possible positions, I, and forbidden squares are the disallowed placements based on the discordance rule. The hit polynomial is related. Its coefficient of use specifically gives the number of permutations with 0 hits, meaning 0 elements land in forbidden spots.
Yeah. So for discordant permutations, we want 0 hits according to the rule.
Precisely. Whether it's the A000183 rule or the 4 discordant rule.
And there was also mention of a Fibonacci sequence related to 4 discordant permutations. That's like Fibonacci's cousin.
That's correct. Fibonacci is some of the previous 2 terms. Fibonacci is some of the previous 3. Yamamoto observed the fascinating thing where Lucas numbers closely related to Fibonacci appear as leading coefficients in rook polynomials for 3 discordant permutations. Then Whitehead's work showed that for 4 discordant permutations, circular, the leading coefficients of their rook polynomials form a Fibonacci sequence.
Wow, okay. That suggests a really deep connection.
It does, a potential structural relationship between the level of discordance and these fundamental recurrent sequences. It hints at underlying patterns as restrictions get more complex.
That's a beautiful illustration of how different math areas intertwine. Getting back to our main focus, A000183, does the OEIS give general formulas or recursions for larger n? Those initial terms jump quite a bit.
Yes, there are formulas. The OEIS entry mentions one involving a sum and another sequence, A061702. More interestingly, perhaps, for n greater than or equal to 7, Vladimir Shevelev derived a pretty intricate recursion formula that actually involves Fibonacci numbers.
Fibonacci numbers again. Seriously.
Yeah. It really highlights the non-trivial nature of counting these circular discordant permutations and underscores those deep connections we keep seeing. Fibonacci popping up here, especially after mentioning Fibonacci for a related problem, is quite striking.
It's almost a mathematical Easter egg hunt sometimes.
Yeah.
And what about the growth rate? Does it explode factorially like the total number of permutations?
Well, there's an asymptotic approximation given by Vaclav-Kotisevec.
Wow.
AN is approximately n times e to the power of -3.
E to the -3, so roughly n divided by, what, about 20?
Yeah, roughly n, 20.08. So it does grow factorially, but it's a significantly smaller fraction of the total n permutations. And that fraction gets smaller and smaller as n increases.
Okay, so to wrap up our deep dive into A000183, we've learned discordant permutations in this circular table sense. Rearrange n items so none are in their original spot or next to it. The sequence starts 0000 because it's impossible for small n, then grows fast. We saw the link to derangements, its key role in the Menage problem, and how stricter cousins like 4 discordant permutations exist, studied with tools like rook polynomials revealing surprising links to Fibonacci and Fibonacci numbers.
Right. And we saw there are complex formulas and that factorial but scaled down growth rate.
That's an excellent overview. It really shows how a seemingly simple question about rearrangements under constraints can lead us to, well, a rich tapestry of interconnected ideas in combinatorics.
Absolutely.
Absolutely fascinating. It always highlights the depth and interconnectedness within math. It makes you wonder, though, how might this concept, this idea of arrangements with forbidden positions in a circular structure, find applications beyond these classic problems? Could we perhaps see analogous constraints, in distributed computing, avoiding certain direct connections, or maybe designing robust communication networks? It certainly gives one food for thought.
Indeed. The fundamental principles of counting under restrictions often find unexpected parallels. The way we think about avoiding certain configurations mathematically can sometimes offer insights into designing real-world systems with specific properties.
Well, that brings us to the end of our deep dive into discordant permutations. Thank you for illuminating this fascinating sequence for us.
My pleasure.
Until our next exploration of the OEIS, keep those mathematical curiosities engaged.